So we've looked closely now at an oscillator which is obeying simple harmonic motion, but the clock starts when it's at its maximum positive displacement. So in the case of this spring oscillator here, it's released at plus A, and then obviously it carries on through its simple harmonic motion. We've looked at the graph. The graph of that motion is a nice cosine graph, and of course we know the equation. Whoops, not a very good line there. And we know the equation is x equals a cosine omega t, where of course omega is the angular velocity of something going in a circle with the same time period as the oscillator. But what about if we started the clock, instead of starting it when it was here at its maximum displacement, what about if we started it when it was here? Okay, so well, we need to see what's going to happen mathematically then. So here's my oscillator again, and I won't draw the springs on, but what we do know is now it's kind of shooting along to the left, so that we're starting the clock at t equals 0. We're saying that it's where this oscillator would have been at a quarter of a cycle in. So in other words, the starting point is going to be there. Well, if we think about it that way, then we can pretty easily draw the graph for that oscillator too. And that oscillator's graph then is going to be like, it's just simply going to be starting from there and going onwards. So let's draw it in. Well, it kind of makes sense that it's going to be like this, which of course we know that shape because it's just this graph moved along. Well, we know that shape. It looks like a minus sign. So actually we've got a different equation now for our displacement. So if it starts at the equilibrium moving left, then we get x equals minus a sine omega t. There's other possibilities too, of course. We could have it starting at its minus a extreme at negative maximum amplitude. So in this case, well, if I put that there as minus a, well, that's like starting the clock at when this has got halfway through its cycle, in other words, when it's over here. And so of course we can also draw a graph for that one, and that graph's going to be different again, and you can sort of see that it's going to be like this. No, it's not. It's going to start at minus a, so it's going to look like this. So at time equals 0, the displacement is minus a. Well, that is a different graph again. It's obviously related. This is a minus cosine. So if we start the clock at maximum negative displacement, then x equals minus a cosine omega t. And the final possibility, I mean, you could start it anywhere in a cycle, but the last one we'll look at is if we just started the clock when it was kind of at equilibrium but zooming back the other way. Well, let's you see if you can draw the graph. Have a pause of the video if you like. Well, clearly this time it's going to be starting at where the top one was 3/4 the way through its cycle. So that one, this graph, is going to look like this shape. And that, of course, is what we know as a sine graph shape. If I can draw a decent sine shape there. No, I missed it again, never mind. And, well, therefore the equation that time is x equals a sine omega t. So in this way, we see that there are 1, 2, 3, 4 basic possibilities depending on where it starts. Now, like I said earlier, there's an infinite number of possibilities, but we're not going to look at more tricky ones than those basic shapes. So you need to be aware that when you see a graph in a question, you can write down an expression for displacement depending on the position at which it starts its oscillation at time equals 0.